Hello students, welcome to Nilachal Polytechnic. Myself Amrendra Mishra. Here in this video lecture, I am going to explain about the fifth number chapter of the subject. The name of chapter is Notches and Wear. These are the contents related to chapter number 5, Introduction, Definition of Orifice, Flow through Orifice, Determination of hydraulic coefficients, their relationship between them, definition of notch and wear, classification of notch and wear, difference between notch and wear, and derive of expression for discharge of water through rectangular notch and triangular notch. Let's come to the introduction part. In earlier video class, we have already studied about the Bernoulli's theorem. According to Bernoulli's theorem, we are going to say that the total energy at any point of a fluid flowing through a pipe remains constant throughout from the inlet to the outlet of the pipe. The application of Bernoulli's theorem we have already studied in chapter number 4. Here in this video, we are going to discuss about that how the flow of water takes place through a orifice, over a notch and wear. Let's come to the first article, that is orifice. As shown in the figure, we are having the head of water is H. This is the container. The container is having a hole is there. The hole is present at the bottom of the tank, through which the liquid will passing through it. So, because of high potential energy, the total pressure energy will be converted into kinetic energy, because the small opening is having diameter less than that of the diameter of the tank. So, what is the definition of orifice? It is a small opening on any cross section, that may be a circular type, triangular type or rectangular type, on the side or bottom side of the tank, through which the fluid is flowing. Generally, orifice is used to measure the flow of liquid, and we are going to measure the rate of flow of fluid. Now comes to the flow through orifice. In flow through orifice, what we are going to say, the water is contained in the container, the liquid is flowing through it. Now, due to the small diameter of orifice, high velocity of water will be coming out from the tank through this small hole. We are observing that while the flow of liquid taking place, there is a point at which the flow lines are parallel and straight enough. After that point, there is a flow direction takes place, and that is towards the downward direction. The point is known as your vena contracta point, and the section is known as your vena contracta section. If we are considering the flow of liquid, now according to Bernoulli's theorem, we are having 2 points, inlet is 1, outlet is 2. Before the water enters to the orifice, the energy is measured at point 1. After the orifice, we are going to measure the total energy at the vena contracta point. Let's consider that how the Bernoulli's theorem is applied to measure the velocity of flow. Now, we are going to observe that there are 2 points, 1 and 2, The jet of fluid means that is the high velocity of water coming out from the orifice. The point 1 inside the tank, the point 2 at vena contracta, as I have already told you. Total energy we have from Bernoulli's equation in terms of head, pressure head, datum head and kinetic head at inlet should be equal to total head at outlet. P1 by rho g, V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square 2g plus Z2. We know that both the point at similar height, so Z1 is equal to Z2. The remaining expression now reduced to P1 by rho g plus V1 square by 2g equal to P2 by rho g plus V2 square by 2g. We know that the pressure energy at point 2 is 0 because it is atmospheric pressure. Similarly, the pressure at the tank inside is, we have P is equal to rho g h. Now H is equal to P by rho g. So the total head at the inlet 1 is equal to capital H and P2 by rho g, that the atmospheric pressure is equal to 0. Putting this value of H and 0 for the value of pressure head at inlet and outlet. So P1 by rho g is H, V1 square by 2g, as the liquid inside the container is at stationary condition, so velocity becomes 0. P2 by rho g is 0, V2 square by 2g. We are getting that velocity at the outlet of the orifice is V2 is equal to square root of 2gh. In this way, we are going to study that the flow of liquid while it is flowing through the orifice, the velocity is obtained as 2gh square root of 2gh. Thank you.